A diffraction grating makes an interference pattern very similar to the double slit. In fact, the equations or the conditions for a diffraction grating are exactly the same. The difference is the bright spots are much more localized. They're very narrow bands of light compared to a double slit. Or another way to think about it, the destructive interference, the dark spots, are spread out really wide. There's a picture of lab data we got this semester. It's tough to tell because I've sort of zoomed in, but the bright spots are quite narrow, more narrow than they were for the double slit. The double slit were more smudges of light, where these are very distinct bright spots. The conditions are the same as well, so our equations, the path length difference ends up being d sine theta, which is the same as dy over L. For constructive interference, or if we're dealing with bright spots, it's n lambda. For dealing with destructive interference, it's n plus a half times lambda. Similar to the double slit, since everything's so evenly spaced, if you know the distance from a dark to dark, that's the same as the distance from a bright to bright. We could use that with the n equals 1 condition. One small difference with the double slit, with a grating, is that the number of lines, the d value we calculate, the distance between them is the total distance divided by the number of lines. We'll work through an example. I'll show you what I mean. Lines. I'll show you what we mean when we get there. Sort of a standard example, we've got a wavelength shining through a grating. A screen is given and the distance between consecutive bright spots is given. We interpret all that. The wavelength is the 540. When we put that into nanometers, that is the same as 5.4 times 10 to the negative 7. The screen is 2 meters away, that's our L value. Consecutive bright spots are 10.8 centimeters apart. That's an n equals 1, and when we put that y value in meters, at 0.108. Since it's consecutive, that makes it a little bit easier. We're going to use dy over L equals n lambda. When you crunch that out, we end up with a d value of 1 times 10 to the negative 5 meters. That's the answer. However, often for gratings, we're curious about how many lines per centimeter there are. To figure out lines per centimeter, we're going to take lines, 1 centimeter. Sorry, the d value is the distance divided by the number of lines. In this case, the distance we're curious about is 1 centimeter. So it would be 1 centimeter divided by the number of lines. We've done the math to figure out the d value, so if we want to know the number of lines, it's the d value we calculated. Sorry, it's the 1 centimeter divided by the d we calculated. Just a little bit of algebra issue. Oops. Yep. These are both in meters, meters, and meters, so the meters cancel out. If we do the math, it's a little bit messy and I didn't word that very well, but we get 1,000 lines per centimeter.